Welcome. Last time I asked this question, given the givens, how can developers and security specialists work together efficiently to produce secure software? I'm going to answer it in this video. First, I'll talk about how security engineers make static systems more secure. Then I want to talk about how to do the same thing for highly dynamic systems. This is more abstract than previous ones, so the last video in this series will show how this might work in practice by showing the specific changes to the puzzles that get at the underlying issues. When designing systems, security engineers like me tell security stories. Here are some. The details aren't relevant to the point I'm trying to make, so I'm going to go quickly. This story talks about how we know that the right code runs in production. Remember, the first puzzler let an attacker run arbitrary code. The second talks about keeping a sensitive value from leaking, as happened in the second puzzler. The third talks about why HTML that includes characters from an untrusted source is safe to run in the browser, which relates to the third puzzle. Once security engineers have a story, we check whether they're true. Where they're not, we re-engineer. I'd like you to focus on the bolded text. Only sources, only available, only called, and only serve HTML. This says that there are some APIs that could be used incorrectly, but we know that they're not. Some APIs come with caveats. If you do this, you also have to do that. Only ever pass inputs that have some property. Only use the outputs in such and such a way. Some of these APIs can't really be made simpler. Writing documentation and hoping that the right people read and understand it is not a strong security story. But limiting the amount of code that uses error-prone APIs lets us bring other techniques to bear. Next, you see phrases like carefully reviewed. Here I'm saying that some aspects of security can't be checked by programs, so we rely on human judgment. Humans are slow, and a small group of experts can't review every line of code in a large program that is rapidly evolving. We need to limit the amount of code that needs review. Most code does not need access to any particular error-prone API, so if we can prevent them from being used except by files on a small list, then we can focus human judgment. We whitelist uses of sensitive APIs, carefully review the uses, and record the judgments in source control. Finally, phrases like finishes building and before untrusted inputs refer to the life cycle of a project. In very static systems, untrusted inputs can't affect some things. Parts of the system go from being mutable to immutable. For example, the size of each instance of a particular Java class is fixed when the compiler runs, which happens before a Java service starts accepting input. An attacker can't add a property to a Java object since there's nowhere to put its value. I've explained some common elements that I've seen in many security stories. I'd like to talk a bit about how we engineer systems so that those stories work. But first, I've contrasted static and dynamic without explaining what I mean. These terms often come up when people talk about type systems, but that's not how I'm using it. I define dynamism in terms of what an input can affect. For example, JavaScript code loading is quite dynamic because string values can be turned into code even when code doesn't use special libraries. CommonJS modules are more dynamic than ES6 modules because a string input can determine which module gets loaded. JavaScript classes are more dynamic than Java classes because fields can be added to and removed from instances and prototypes after the class declaration finishes. But new-style JavaScript classes are less dynamic than old-style code that added to prototypes because dynamically setting the prototype field cannot change a supertype. Using that definition, I'd like to talk briefly about how security engineers approach security stories in static systems and how we might adapt to highly dynamic systems. In a static language, a developer makes a change and recompiles their code. We tweak the compiler, linker, and run analyzers to get information about problematic code patterns and uses of dangerous APIs. That information is available to the code review tool. If there's a new use of a problematic API, we loop in a domain specialist. They might approve the use, then we record that decision in source control, or they might recommend a safer library. Done well, this makes it easy for a small security team to intervene in a very targeted way and help developers produce secure, robust code. This works well for very static code because there's this explicit step, the build stage, where we know what potentially dangerous functions code could call. Here on the left, you can see some of the phrases that keep showing up in security stories. By tightly integrating with the toolchain, We can check requirements of the form only these connect to that. There are also often language features like private that help. We capture human judgment and source control and check that only reviewed code does certain things. Tight integration with code review tools detects when review is needed, auto-assigns reviewers, and makes this whole process pretty smooth. We avoid problematic uses of reflection by making the build pipeline more flexible. For example, we can automatically generate code to sync databases and objects and prevent SQL injection. These techniques don't work as well if you don't have a tightly integrated build system or are working with an uncompiled language. This is one reason why Google has favored front-end code in Clojure and Quit, which feel like static languages. I'd like to propose an alternative. Instead of making JavaScript into a mostly static language with unsound tools, let's focus on enforcing security stories while preserving JavaScript's strengths. First, instead of reinventing static data access like public and private using unsound linters, let's make access decisions dynamic. JavaScript has many fine module systems that are now widely available. Security engineers like me can check many stories that hinge on only these talk to that. Representing module identity as a runtime value makes that straightforward. This goes a long way to addressing many of the underlying problems in the web puzzlers I presented. Preventing unwhitelisted code from invoking the parser on a string addresses the first puzzle. If the code that populates the email template can access the text of the password reset link, but other code can't, then I have addressed the second puzzle. I can fix the third puzzle by making the safeness of the values in the legacy names table part of those values so that the HTML template can decide whether to escape purely by looking at the value. I'll get into more detail in the next and last video where I explain in detail how to reify module identity. To reify means to represent a concept as an object or value. For dynamic systems, we also need a way to enforce human judgments about code. Once we have a concept of module identity, we can represent human judgments as lists of modules. We need one more thing. In Node.js and maybe on the browser, built-in modules connect code to the outside world, so some imports connect us to power that might be misused. If we want to bring human judgment to bear on how to wisely use powerful tools, then we need to be able to judge imports. Very few modules need direct access to child process, for example. But everyone that uses a dynamic require or import could potentially load it. If it's important to keep eval away from most code, and it is, then it is important to restrict shell access to only modules that need it to do their job and which take appropriate care. This pattern repeats itself. In Google code, there are unsafe APIs that need to be used carefully. There are other APIs that wrap them carefully to provide safe abstractions. Very few modules need access to any particular unsafe module, but some do. We bring human judgment to bear. Those who understand how to use the unsafe APIs vet code that would use them. Many times we talk to the developer and find that safer APIs actually do what they need. Finishes before arguments work really well for static systems with a well-defined lifecycle. First you compile the code, then you link it, then you load it, then it looks at flags, and finally it starts talking to other processes. I don't think dynamic systems really need this tool. If they do, an application could define a lifecycle, represent lifecycle stages as values, and allow the main module to advance from the current stage to a less privileged stage. In contrast with the workflow diagram earlier, there's no static compiler or linker that knows which code uses which sensitive APIs. There are many tools out there like Clojure Compiler, Babel, and Webpack, which do similar things, but like linters, their analyses are optimistic. Instead of relying mainly on unsound static tools, I think we should prefer dynamic enforcement that fails safe. We can collect a lot of useful information by running tests. A module loader runs when one file requires imports or sources another. The test runner can build a dynamic import graph, which shows which modules load sensitive modules when the system is not under attack. That graph can be automatically checked against a whitelist in source control. Running the test before untrusted inputs reach the system turns up any missing whitelist entries. Continuous integration tools can loop in a human just the way we do for static systems. In production, the module loader then enforces the whitelist. If, for example, the colors module tries to load child process, which didn't happen during testing, the module loader might throw an error or substitute a less powerful module with an equivalent interface. Here's an example of what I mean by a module import graph. This was derived by adding a few lines of code to the node runtime. It shows the import graph for a very simple Node.js program that used a variety of conditional and dynamic imports. There's an arrow for each require from the module that does the loading to the module that is loaded. Package.json specifies index.js as the main module, and here's the code for index.js, which loads modules dynamically, lazily, and optionally. So in the static case, compilation fails early on a violation. In the dynamic case, it fails safe in production, but test suites with good coverage still get you the early failures in most cases. In both cases, this meshes well with continuous integration to make efficient use of targeted human judgment. I hope I've convinced you that we can improve software security in dynamic systems. Here's what I've asserted in a nutshell. Limiting access to error-prone APIs limits what an attacker can exploit. Strong security stories depend on knowing which code can access which powers, but in highly dynamic systems, we can't reliably know what powers are accessed until the code is running in production. Product teams need to be able to control access. Most pieces of code only intentionally use a few of the many powers available. So we've got to move past binary trust decisions. Few want to trust their whole program to call new function, but that's what happens. It'd be better to trust some modules with that power. Unless human judgments about code live alongside the code, and unless those judgments are enforced, security stories become obsolete as code changes. But lightweight policies that are enforced at runtime stay in sync with code changes. Many security stories are easier to enforce if the identity of a critical piece of code is available as a value. Built-in modules affect the outside world. For example, child process can fork a process as the current user. Module loader hooks can strengthen security stories about the outside world. This video was different from previous ones. It was heavy on theory and light on actual code. In the next video, I'll get concrete again and show how to address the core problems underlying each security puzzle by separating the correctness of the majority of code from the security of the system. Thanks again for watching.